So you have learned all about nuclear fusion, fission, and also how to use the decay law to describe the decay of radioactive nucleus. But did you know, once upon a time, well, not too long ago, in 1920s and 30s, people used to glaze ceramic, meaning we will put a shiny layer of uranium oxide on the ceramic plate. Okay, so watch what happens when we place a Geiger counter near the plate. This is normally from the 1920s to 30s, because after that World War II happened, and people wanted uranium to make other stuff such as bombs. All right, so let's hear what's going to happen when he turns on the counter. Listen to the crackle. So that crackling sound that you hear is something that we call a count rate. So the number of nucleus that is decaying per unit time, you can hear the crackling because it creates an ionizing radiation, maybe alpha, beta, or gamma. And the ionizing radiation will ionize gas inside this counter, setting up an electric field. So the sound sounds a lot like sparks. If you're interested about how a Geiger-Müller counter works, go check it out on Google. All right. But in this video, we are going to think more about count rate, or how to use maths and equation to describe the crackling sound that you hear. If you're ready, let's go. So this is not an unfamiliar picture. All right. We have looked at this thing before, and I've already explained to you that this, you could listen and watch the decay. So once again, we are looking for count rate, the number of clicks per unit time. And as you can probably tell, if I increase the number of isotopes to 1,600, this is what happens. Listen to the sound. So this second one, you will hear more clicks per unit time. So this clicks per unit time is what we call as count rate or activity. I'm now going to write our notes now. So activity A, which is that clicking sound, right, is defined as the number of nuclear decay per unit time. Right, so this activity A is defined as number of nuclear decay per unit time. So A is actually equal to our good old dN dt. All right. So when we say A is equal to dN dt, now you have the equation for N, right? Remember, we could modify from this equation to write an equation for N. So now we have to differentiate N all over again. Okay, so we'll do that. All right. So this one will be N is equal to N naught E negative lambda T. Okay, so right now what we'll do is we will differentiate this thing. Okay, so I'm going to put this in here, d dt. Okay, and then I'll put a bracket here. This is N naught E negative lambda T. Okay, and this one is decay per unit time. So nuclear decay means the number of nuclear decay will decrease. Okay, because if we keep saying how much decay per unit time, it's something that is changing with respect to time. And we would like a number here to represent how many decay happens in a given fixed period of time. So because there is a decrease in the number of nuclei, so we're going to have a negative here. Okay, so once again, the negative here is to show N decreases with time. Makes sense, right? The number of radioactive nuclei be less and less as more and more decay happens. So we're going to differentiate this. So it's something that you may or may not be familiar with, depending on whether you do maths, all right? But by differentiating this, I will get A is equal to, all right, so N naught is a constant, which I will plug out. Okay, and what is left is differentiating E negative So we're differentiating this lah. D dt bracket E negative lambda t. Now what happens when you differentiate an exponent? You will get back the power again. The power will travel down. So this negative lambda t comes forward to multiply. So what you have now is n naught times lambda. Or I guess if I rearrange it again, it will be lambda n naught. Okay, lambda n naught. And then this will be E negative lambda t. So you differentiate lambda t, you will get lambda. Differentiate negative lambda t, you will get negative lambda. The negative lambda bring forward to multiply. You get positive lambda. All right. Okay, so I'll write that step for you lah, in case, you know, people are not used to this. Okay, so you differentiate, you bring forward this power. There, this power here. All right, so you differentiate once, the power go down, so it becomes here. All right, don't forget we have an n naught. It's going to have it at the back here. And you differentiate this, you will get E negative lambda t. That's the beauty of exponents. No matter how many times you differentiate, you still have this thing at the back. So right now what we will have is A is equal to lambda n naught E negative lambda t. But you see this lambda n naught is constant, right? So this one, I will just call this A naught. So I will have A is equal to A naught E negative lambda t. Hey, wait a second. This is very familiar, right? Because we have seen this before, guys. That N is equal to N naught E negative lambda t. So this X, it can be N, it can be A, all right? So A naught, just in case you need it, what is A naught? A naught is the initial activity. So when you first started the reaction, when I first played the simulation, the first number of nucleus decay in a given unit time. Okay? And then A, because A here is the activity at time t. Okay, so your variables here are A, this is your activity at a given time t. All right, just like when you have this one, this N is equal to N naught E negative lambda t, this will be the number of undecayed nucleus at time t. All right, so hopefully you're okay with the equation, feeling a bit more comfortable and confident. Okay, so one more thing about activity besides the definition. Activity has a unit of BQ. Okay, BQ, the full term is becquerel. BEC QUEREL. Okay, becquerel. And actually the SI unit here means, for base SI unit, this is second negative one. All right, so the activity unit will be becquerel because it's number of nucleus per unit time. We also call this the count rate. So how many nucleus decay in a given time. So we're going to now draw the decay curve. This is activity against time. So this axis will be A bracket BQ for becquerel. Maybe, let me zoom out a bit. This one here would be time in second, or bracket second. Okay, so this one is pretty similar. So we're going to start off with A naught. And after one half-life, so let's say this is T half. And let's say you reach here is 2 T half. And so you reach here is 3 T half. Okay, so we're going to start from here, and then in one half-life, it will drop by half. This one will drop by half. This one will drop by half. So this is the kind of shape you expect to get, still the exponent shape, because the equation kind of looks the same, right? See? So because they have the same equation, they should have the same shape of graph. All right, and the only last thing that I want to talk to you about regarding this, let me find a place to squeeze this in, is that from this definition, if I want to relate activity to number of radioactive particle, I will use this equation. A is equal to lambda n. And I will argue that this is actually quite useful. So if you have activity, you can find the number of particles. If you have the number of particles, you can find activity, provided you know the half-life, which will help you find your lambda. Don't worry, I'll summarize all these important equations together. Okay, so when you think about radioactive decay, right, or that clicking sound or that count rate, what exactly are we measuring? Let me show you something more. Okay, so what we are talking about just now about becquerel, okay, is the first one. We are measuring the radioactive decay. Okay, so it's 1 becquerel means 1 decay per second. 1 click in 1 second. Okay, so this becquerel normally is done by calculation. All right, but of course, sometimes we want to measure ionizing radiation. For example, of course, if you are nearer to a particle that is ionizing, let's say, for example, if an alpha particle and it's right in front of your face, of course, that will hurt you much more than, let's say, you are like 1 meter away. So, of course, the inverse square law will apply. The further you are from the radioactive source, the less harmful it will be. Because radiation is basically saying that I am alpha particle, and if I encounter another particle, I will take away its electrons. Ionizing. I will make the particle an ion. So this is how it disturbs your DNA. The ionizing particle pass through your body, ripping apart the electrons in your DNA. Okay, so of course, as it travels a distance, there will be some scattering because it will collide or it will interact with the air particles. There will be some absorption, maybe absorbed by your clothes, by your door, by the wall of the building you are in. Okay, so ionizing radiation strength from a point source decreases with the distance traveled, and also depending on the medium that is traveling with. So if, let's say, you look at Chernobyl, they build a containment to make sure that the leakage is not going out. So this will all affect the radiation. Okay, detection, we use the Geiger counter. Okay, and the quantities that we use for this reason is sievert. Sievert is a more common quantity, but 1 sievert is 0.1 becquerel, so it can be converted one. Okay, and so there are different units. We are sticking to this becquerel because this is SI, and it's also named after an Englishman, so it's the SI quantity. Okay, and in this case, right, both dose and counts are used. Okay, so it depends on who is using it and what they're doing it. So this one is all later. If you study more physics, or if you learn to use radiation either in the hospital to treat cancer, to sterilize medical equipment, or if you're doing this for other things, because look, radiation got plenty of usage. All right, so I'll show you the usage of different types of radiation. This is like a throwback to your AS, okay, your alpha particle, beta, and gamma. But I want to look at the uses here, because sometimes in your A2, your paper 4, we will use decay law, but using it in the context of all these various forms. For example, alpha is mainly used in many smoke detectors. Okay, and also we use it to power some pacemaker in the heart. And also the space probes. It's not dangerous, man. You put alpha radiation inside the heart pacemaker. Alpha's penetration is bad. So I'm pretty sure we can contain the alpha particle within a closed container, provided there's no leakage. Okay, what about beta? What is beta used for? So beta has the most common use one. We use it as tracer in medicine to image the body, because beta radiation kind of interacts slightly differently with X-rays. There's a whole entire field of sciences here, okay? We also use it for cancer treatment. So this is why I think radioactivity is a pretty interesting chapter, because you can see how it's used in different parts of the world. And also, later on, you know, maybe you will need to know how to detect how much dose you have received in your body. So if you need, you can take a break. Because people who work with radioactive particles, part of their annual leave is that they can take a break if they're overexposed to radiation. So on their ID tag, there will be a sensor there to tell them, oh, you are overexposed, the recommended dosage, take 6 months off, paid leave to cool off. Very nice, right? Okay, in the industry, we use this to find leaks in the underground pipes and then to find out how thick the material is. So this one is because of attenuation. When radioactive particle travels through the distance, it will decrease in intensity, or rather it will decrease in count rate. But more importantly, we also use this to find leaks or cracks in the building. So if let's say, right, I have a 50-floor building and somewhere there's a leak and I don't know where the leak is, I can't open up all the pipes in a 50-floor building, right? So what I'll do is I'll put a tiny bit of beta radiation inside the pipe, and as the pipe flow through the entire building, I will bring my Geiger counter and walk around and listen for the tit, the crackling sound. So the place or the level or the room with the largest crackling sound, that is where the leak is, lor. Does that make sense? Okay. Same thing as well. We can also use this to measure thickness. Okay. When it comes to measuring thickness, how it looks like, maybe you need a picture. It looks a little something like this one. Let me show you. Okay. So if let's say you want to measure thickness of material, it looks like this. Okay, so for this one, you see, this is the material that we want to use. Okay, so there's a radioactive source here and there's a detector here. If let's say the material is suddenly too thick or too thin, the meter, the crackling sound, the becquerel reading will be different. So it's sent to the computer. The computer got some op-amp1, there's some amplifier here, inside here, will feed back into the system. Maybe you need to pause the machine to adjust the material. Maybe there's a way to adjust the roller that's rolling out the material. Maybe this is a sheet of metal. Okay, so this is the way that you can use it to determine or gauge the thickness of your materials during manufacture. Okay, so this is one of them. And finally, our good old gamma radiation, low ionizing, high penetration. Because of this, we use it also for cancer treatment and also for sterilizing things in the lab. Okay, especially medical equipment and also food. All right, gamma ray detection is also used by a number of telescopes to produce images. So we are looking at things by analyzing gamma ray. All right, so radioactive particles have, and this radioactive radiation has so much usage. If you're interested, there's always the internet that you can find yourself in. Okay, and also, right, at the same time, the most important thing in this subtopic is that you know how to apply the decay law for calculation. All right, so we will give you different scenario. Maybe we are treating cancer in this year, this variant. Maybe in next variant, we are trying to measure the thickness of the material. Maybe in the subsequent variant, we're trying to figure out how long is it safe for this fuel rod to be buried underground. So plenty of application. And as you try out those past year questions, take some time to read and also to understand the many benefits and uses of radiation besides weapon and nuclear generator, power generator. Okay, so as a summary, because I still have a bit of time, I'm going to summarize all the important equations here. And for those people who may need it, okay? So number one, we learned that this thing called spontaneous and random. So make sure you know how to write out the differences between these two. And number two, from the equation given in the formula sheet, okay, I will bring this here. Because normally by this point in time in your A-levels, maybe you're thinking my brain is kind of full. I would like to refer to this instead. Okay, so number one, just based on the first equation, I know N is equal to N naught E negative lambda T. Okay, and lambda can be calculated from ln 2 over half-life T half. This is important to know the proof and also to be able to understand what lambda is. Okay, so you need to know the proof. So you also need to know the definition, which is probability per unit time, probability of decay per unit time. Then from here, your A is equal to dN over dt. So what we have now is A is equal to A naught E negative lambda T. Okay, and because of this, we can also convert between A and lambda. A will be equal to lambda n. All right, this one is oftentimes forgotten. And because we have number of particles, right, don't forget that we may have to use the mole concept. So if you're kind of a bit rusty with the mole concept, maybe it's time to pay it a visit. Okay, so this one is number of particles. So the mole concept. All right, so to help you use this equation better, okay, we're going to now jump into the examples, which will be another video. Okay, and I'll see you there. But I think this is the end. If you're watching the theory, this is the very end of your A2 syllabus, unless you have not learned certain application or communication chapters yet. So strongly encourage you to think and reflect about the physics that you have learned so far. It's been a long journey, and you have done very well for yourself if you've been trying your best and learning alongside with us. I'll see you in the next example video. Okay, take care. Bye bye.